Hello everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain. I'm an applications engineer here at EasyPower. And today we're beginning the first of a four-part series focused on protective device coordination. And for the most part, we're trying to start at the ground level, pardon the pun. And today in particular, we're going to be dealing with some very basic system landmarks, if you will, and the tools that we use to look at coordination. And we'll get into more depth as we go farther into the series. So again, welcome to all. We'd like to start with a poll question or two. If you wouldn't mind participating, we'd appreciate it. First poll question is regarding a typical facility. How long since coordination was updated in facilities that you're familiar with? So there's no right or wrong answer, just some feedback. We're trying to get a bead on kind of the perspective you're coming at the discussion this morning or today. The webinar is being recorded and will be posted to the website as a video along with PDF copies of the slides. All right, let's leave this about another 5 seconds. Looks like we're close to a quorum. All right, here's how folks have responded. It's like a pretty wide distribution. Now, realistically, you don't have to, theoretically, you don't have to do a coordination study that often because it's part of the initial commissioning of the building and the equipment. But if there's any chance that anything was changed or that loads have changed or that anyone has replaced fuses, there's a need to potentially see if anything has been modified. So the second question is, has your facility experienced transformer or other equipment failures due to improper coordination? Again, this is just a curiosity. There's no liability or obligation. And hopefully the answer is yes. I'll make that no. Sorry, didn't wish anybody ill will. Okay, let's give this another 5 seconds. And here's where folks have weighed in on this. So yeah, the looks like almost 20% and possibly more could be the root cause of the problem. So that's why we review this, and especially with a lot of junior engineers coming into the market, there's a need for reviewing this material periodically. So today's agenda basically is to talk about the purpose of coordination and some basic guidelines of standards that are used to make an even footing as far as how the analysis is done and how we can work with manufacturers to understand the workings of the equipment that could be fairly expensive and difficult to deal with if we don't have more information about its operation. Then we're going to get into the available tools. First and foremost is understanding what's represented on the TCC plots, and then how EasyPower controls the faults that affect the analysis, and then the parameters specifically for transformers and motors. So again, we're barely scratching the surface, but it's all vital information for the overall topic. So protective devices have a number of particular functions in system design. First and foremost, they protect the equipment from excessive temperatures and excessively high loads or faults to minimize equipment damage. They often reduce the risk of fire and explosion and potentially reduce the risk to personnel. Often it's required as part of a legal document, specifically the code when we talk about commissioning a plant or a new facility. And then frequently it can be part of an insurance coverage issue to make sure that you have the proper devices in place to protect the equipment. Now, the term coordination is slightly different, and most often we're talking about what's referred to as selective coordination. But in a coordination study, the intent is to look at the characteristics of the protective devices and determine optimum device settings to ensure that the system reliability is improved, and that is, subject to the protection of the system components. We want to achieve minimum interruption for different types and magnitudes of faults and overcurrent. So acceptable selective coordination is obtained when a minimum amount of equipment is removed from service based on a remote fault. Now, often selective coordination will result in higher arc flash incident energy, so we'll find that there's always this offsetting balance or offsetting requirement that if we want to increase mitigation, then there's a penalty we need to pay potentially in coordination, and vice versa. Coordination, again, potentially means higher incident energy, especially at the upper elements, because we're having to set their timing slower to allow the downstream elements to work first. And it goes without saying that this is usually done in conjunction with a short circuit study. So here's how something like this works. Here's our one-line diagram, and we're considering selective coordination for loads that are going to be at the end of these feeders. If we have a remote fault, let's say I have a fault on this particular bus or load, that fault current is going to be sensed or felt by 3 different protective devices. The primary fusing in the transformer, the main breaker to this distribution panel or switchgear, and then the feeder breaker that's closest to the load. So ideally, realistically, any one of these breakers or protective devices should trip at some point. The goal is to make sure that this feeder breaker trips first, and thereby preventing the loss of energy or control to the rest of the operations. For instance, if we lost the primary fuse and the whole plant goes down because of a simple fault at a small motor, it would be onerous as far as the amount of lost productivity for something that could have been avoided. Well, the tool that we use to verify this and to make this adjustment or recommendations is called the time current characteristic curve. And this mechanism has been around since the early days of switches and breakers, and it is used and specified for devices such as transformers, loads, overcurrent protective devices, and even cables. And what it does is allows us to predict safe operation and potential areas of damage by comparing the short circuit current or even the operating current in a particular load to the upstream devices. Now, it's not all that magical. These, similar to every other plot that we've ever seen in our education, the difference being we have current on the horizontal axis and time on the vertical axis, and we are in the process of doing a short circuit study. We're predicting the current that will occur on a specific bus downstream of a downstream fault. Now, the term inverse curves is applied to overcurrent protective devices, and it basically means the higher the current, again, the current's on the horizontal axis, then the quicker the response time of the protective device. Now, just for this illustration, we're not going to get into the details of these types of devices, but this gray plot is a typical curve for a multi-case circuit breaker. The blue plot is a typical curve for a low voltage power circuit breaker. And then the red or rust colored plot is a typical profile for a fuse. If we, in our short circuit study, determined that the fault current at this bus was 5,000 amps, then we would plot that value in the vertical direction, intersecting with the 5,000 amp point, and where that curve crosses the upper or right-hand boundary of the trip curve for that protective device, that tells us what the trip time is, or what the time to clear the fault will be if that equipment were utilized. So for instance, at 5,000 amps, it looks like the multi-case circuit breaker would trip in 20 milliseconds. If that didn't clear, then a low voltage power circuit breaker will trip in 300 milliseconds. And then finally, if neither of those cleared, then the primary fusing looks like it would clear in about 80 seconds. And again, its primary function is to prevent a fire, usually in the transformer. It's relatively easy to see or to be able to make the statement at 5,000 amps, this system is series coordinated. Question about whether or not presentation slides will be available. Yes, we'll make a PDF copy of the slides available, and it'll be posted at the same time the video is listed on our website. Everyone will receive a notice on that. Now, what we're going to focus on is protecting specific elements. And transformers are the most expensive, usually the most expensive element in a system, and they need to be protected from overloads, from internal faults, through faults. The transformer damage curves only deal with through faults, not internal faults. And basically, if you have an internal fault, the equipment's already damaged. There's already a short or an open in the transformer, and then the TCC itself is not particularly useful. Now, a through fault basically is defined as an external fault on the secondary of the transformer. And it's just a fact based upon the turns ratio that the windings see very high current when we have an external fault. For instance, for a 5% impedance transformer, the current can be as high as 20 times the full load current. And this especially is an issue when we're talking about heating and magnetic forces, because they are based on the square of the current. And so for current that's 20 times the full load current, the forces from heating and magnetic elements or current could literally be 400 times what normal stress would be. So through faults, again, prevents overheating of windings due to current. It also prevents mechanical damage due to the magnetic forces, because windings are inherently repel each other. And if we see a large surge of a fault, that large magnetic force could be mechanical damage to the core or to the windings themselves. The ANSI standard C57.109 is utilized or has been developed to define transformer damage curves and define the magnitude and duration of through faults that a transformer should be able to withstand. And so there are tables and plots in ANSI C57.109 similar to this, where it gives us a definition of certain categories, both for single phase and three phase, and then different size ratings, and then whether or not they are subject to or should be considering frequent faults. And this will make a little more sense when we see the TCC curve. But basically on the larger transformers, the susceptibility to frequent faults is more significant, and consequently they're only allowed 5 frequent faults during the life of a transformer, whereas on a category 2, potentially it could survive 10 frequent faults over its life. Now this again makes more sense when we look at the protection curves or the TCC curves. So this is a typical damage curve, and again what we would do is predict the current in an individual downstream bus, and then that tells us whether or not it's going to intersect the damage curve of the transformer. So this plot is based on an ANSI C57.109 oil rated transformer of 1000 kVA with an impedance ratio of 5.75%. Again, this is all information that's entered during data collection, and so it's important to get the data accurate when we're doing data collection. The upper part of the curve is referred to as the thermal damage section, and we'll see where that's indicated in the plot. And then the mechanical damage section is at the higher current range, and it's offset from the 100% damage curve. So again, we're protecting at lower currents, longer time exposure from thermal damage, and higher current for shorter time was protecting or avoiding mechanical damage. So the protection, and we're going to go into EasyPower here, and I'm going to show you where this is set up. But protection based on the frequent faults is conservative. And let's kind of do that, show where that's coming from. So here I've got a one-line diagram with 3 different transformers of the different categories that they give us descriptions of. So a Cat 1, again, the specifications are critical because that's going to define the type, class, and rating of the transformer. Now, taking a step aside, one of the things that we recommend during data collection is to take a digital image of nameplates, and transformers are particularly valuable. The tool allows us to connect a image of a transformer, in this case, and carry it with the project. So at any given time, we can look at the label or the nameplate and verify that we've got the correct data entered, or that someone originally set up the one line has been properly recording the data. So again, that's just a feature of EasyPower. Now that label or that nameplate is not for a Cat 1 transformer, so it was just for illustration. Now the point I'm trying to make is that once we've got the data entered, when we go to plot the TCC curves, by default, all 4 of these check boxes are filled in. And what that gives us is a TCC plot that looks like this. The module that we use for coordination, we refer to as protection and coordination, and it allows us to save TCCs. So I've already created this TCC plot showing all 3 transformers. And in this case, they're color coordinated. I'm not sure you can see that on the screen. So real briefly, what's noticeable right off the bat is that this is a straight line, and this is a square, what's loosely referred to as a Z curve with a jag in the middle here. This is referred to as a frequent fault curve versus the Cat 1 transformer, which doesn't have, by definition, frequent fault curve availability. So if I go back and look at the setup, we're asking for a frequent fault curve in the smaller transformer, but because ANSI C57.109 doesn't have one, there's no jog in this plot. Whereas we go to Cat 2, we're asking for a frequent damage curve, frequent fault curve. If I uncheck that box, watch what happens to the plot, this middle one. So what this means is this is the 100% damage curve. I never want to have any current time plot be up and to the right of this dotted line. However, on frequent faults, this transformer should survive whatever is listed in ANSI C57.109. I think it was 5. It should survive 5 excursions of this particular part of the curve. The bottom line is, if we protect the transformer even to this curve, it's most conservative, and we're ensuring that it never gets to the 100% damage curve. Let me kind of check a couple more keystone points. We'll talk about the unbalanced derating here in a second. We'll talk about magnetizing inrush in a second. The damage curve is again plotted on a certain range. And right here we're showing it from 2 seconds to 500 seconds. The maximum range on the current is, well, let's take that a step back. Right now we're plotting everything at 480 volts. So all these currents are referenced to fault on the 480 side. If we wanted to plot them with reference to 13.8, the tool allows me to change my reference point, and it skews all of that current to the left. And now we're looking at equivalent current in the 13.8 range. So if we were setting primary protection for these devices, this would be the current that we're expecting to measure, 697 amps in the 13.8 range. And that's all being illustrated here in the range that we're showing for 13.8. Now we talked about the inrush, haven't talked about it yet. Inrush is also based upon the parameters that we've input into the tool. And in this case, typical values are 8 to 10 times full load current and a 6 cycle time delay. So what this means is if we're going to have protective devices set up for the transformer, they don't want to be sensitive enough to be tripped by the current inrush when it's first energized. Now this applies only to primary protection, and I think I got more information on that as we're going along. So I mentioned my 3 transformers that I've shown here. There's a delta Y with the Y grounded, delta Y with the Y grounded, and they're all the same. The problem comes up if I have a delta Y fault on the secondary side that's a single line to ground. And the per unit seen in the primary protection, it's not the same current as seen in the secondary winding. For instance, if we're looking on a phase-to-phase comparison, through faults on a 3-phase fault is equivalent, but if we have a single line to ground, it's not equivalent, and this is the reason. So in normal operations at full load on the Y side, if we're measuring 1 per unit current, it corresponds, at least in magnitude, per the turns ratio to the 1 per unit on the primary side. But it's not a direct correlation. It's because we have 2 phases involved, and each one is 0.58. So my total per phase is going to be a 1 per unit that corresponds again to the turns ratio in the secondary. Now that's all well and good if we're talking about 3-phase faults. However, if we have a single phase fault on the primary, so we have a through single phase fault, and we're trying to protect or sense it on the primary side, then we can see that if we only have a 0.58 per unit current, that corresponds to a 1 per unit fault on the secondary side. So ignoring the load current, the primary relay or fuse will only see 58% of the per unit current that we've been monitoring for 3-phase faults. So what that means is we need to offset that damage curve by 58%, and this is what's referred to as an adjusted ground fault seen from the primary. So let me see if I can illustrate that. I've actually saved that plot. So what we're talking about is single line to ground and ground protection. And the fact that we have to consider this rating, the 58% lower rating when we're monitoring primary current. So here we have actually three situations where we have high resistance ground as indicated by this resistor in the neutral connection on the Y side. Here we have a hard ground, and here we have a delta Y with no ground. Probably should have done a delta delta because they're similar. All right, so let's look at the hard ground first. What we see when we look at the parameters that we've set up is that we've checked this box which says plot the unbalanced D rating of 58% for the TCC. And so that's given us this jag in the current. Let me uncheck it and see what it looks like. So if I uncheck that block, again, it takes away that part of the curve. Now, what does it hurt? Well, it doesn't hurt anything as long as we're trying to coordinate for three-phase faults. But as soon as we look at a single-phase fault or a line-to-ground fault, then that 847 amps isn't compared. Let's see if I can. Well, we'll see it when I use my fuse. Let's see if I can pick it up this way. Okay, so by putting the fuse in there, the tool is showing me the maximum current through the fault of 847 amps. So that 847 amp current corresponds to 934 amps asymmetric. If I set this as my reference for scaling, that current is the current that's going to be experienced by the transformer, and I want my protection to fall between, or at least high enough, so that it never exceeds, that current doesn't exceed this second plot. I did a poor job of explaining that, but the point is, normally on a three-phase fault, I could set my current up to protect against a three-phase fault and never hit the frequent fault curve here. But on a single line to ground, which is what we're looking at, and a fault here, that 847 amp protection needs to be reduced so that it doesn't exceed this derated curve. Okay, I could have done better on that, but let's see what else I wanted to do. I do want to compare all three. So there's a difference. Yeah, so I want to look at the three plots for the high resistance ground, right? Having this resistor in the neutral leg or the ground leg of the Y side guarantees that the maximum current on a fault here will not exceed 10 amps. So a fault here we're showing 10 amps, or 100 amps, I'm sorry, is 100 amp resistor, which will mean we have a 2 amp fault on the primary, and you'll notice we don't show a derating curve. Well, that's because this 2 amp protection, this 2 amp fault, isn't anywhere on threatening to damage the core itself. But I do need to set if I have protection monitoring this, I do need to set my protective relay or fusing to trip at something less than 2 amps. Okay, let's see if I want to go back and look at the hard ground we looked at. The other one I want to look at is the no ground. So when we have an ungrounded system and a three-phase, single-phase fault to ground, again, we have no derating current because there's no ground current. By definition, we have an ungrounded system, and so there won't be any ground fault current to measure. If we go back and look at a three-phase fault, then again we're looking at the frequent fault curve, and we set our protection so that we're not. We'll get into this more for transformers in the next couple of weeks, but I'm just trying to talk about the milestones that's being displayed for different types of transformers. Hugely valuable information, but it's important to know what type of fault I'm applying and where I'm looking at the current for protection. So this whole derating ground fault, we're talking about the primary protection and a single line to ground where we have to derate the curve. Now, part of the National Electrical Code is overcurrent protection. Again, we'll get into this in more detail, but this is table 450-3, and talking about the primary protection and secondary protection. These numbers represent the maximum protection for a fault. On the primary side can be as high as 600% of full load current. And that doesn't mean it have to be, it just means at a maximum, that's where we want to set it. And when we get into coordination, this is something that will come into play. And again, this is part of the National Electrical Code. I referred to the Inrush plot earlier, but what it amounts to is that during initial energization, there's a potential for current and a host of different harmonics to be launched at the time the transformer is powered up. And that's, as we saw in the data block for the curve, that's represented based upon some multiple of full load current and some delay time. In this case, I think it was 0.1 seconds. And we want to make sure our protective devices will not be sensitive to that particular current and time element. So for primary protection, we must have the protective devices up and to the right of the Inrush plot. All right, so then the last thing I wanted to cover was motor time current characteristic curves. And just like the transformer, all this is based upon data that we collect when we're drawing the one line, or we're collecting data for the model in EasyPower. And the TCC looks like a chair for a motor starting curve, at least an induction motor. And these all have relevance to parameters in the setup. We'll get into EasyPower and look at that. But what we're looking for, first of all, is acceleration time. Once we apply across the line voltage, the motor is at what standstill. That's referred to as a locked rotor condition. And so where this vertical line extends down and intersects our axis, that's referred to as locked rotor current. And that current will be normal or acceptable until the motor is accelerated. So the time of this particular cross member is referred to as acceleration time. So it looks like we have an acceleration time of about 5 seconds on this motor and a locked rotor current of looks like 4,000 amps. Now, there's a tail that we refer to as the asymmetric offset, and it's very similar to Inrush, and it's based upon worst case. What we're plotting is worst case on the phase as we energize the motor and the current, and also we'll look at EasyPower and we'll see where this is set. But again, that needs to be accommodated when we're setting protective devices to differentiate between a normal start and an abnormal start. Any time current plot on the left side of the chair is considered a normal starting. Any time current plot to the right side of the chair would be considered an abnormal start, potentially abnormal start, and we would want to have protective devices that came into play. Now this slanted stubby line is the thermal limit stall time curve, and any time current exposure to the upper right-hand side of this straight line means the motor is susceptible to damage, physical damage, at that time. So this is one of those limits that you never want to exceed. And then the vertical intersection between our motor starting curve and the upper axis looks like it's about 600 amps. That's the full load current as defined by the setup of the motor. So now that we've got all that kind of defined, let's go back and look at EasyPower and see what we got. So most of this information, well, again, the slides will be available on the website when we post the video. Most of this information is also on other webinars that we've done specific to motors and to protective devices. So again, in Database Edit, I've found the motor icon from the equipment palette and put it in my system, in this case 480 volts. If I open the dialog box for the motor, and again, there are times that I may want to actually take an image of the motor nameplate and save it. But the primary thing that the tool is looking for is horsepower. And so once I put the it's indicated when we set it up with a red exclamation point. Once I put the horsepower in there, the tool calculates my kVA rating. If I want to plot the full load current, I can click this little calculate button, and it looks up on the NEC tables the full load current for a 50 horsepower motor, and then the tool recalculates my kVA. So if we skip that part, you can see it recalculates the kVA based upon the horsepower, efficiency, and power factor. So that's the specification tab. When we go to the short circuit tab, this X over R will be blanked out. In mandatory, the tool will calculate the X over R for me. And then when I go to the TCC curves, I indicate what type of starter we're using. Again, we're plotting a full voltage 50 horsepower motor. That's an individual motor load. The locked rotor multiplier is 6 times. And again, this is a default value. If I know my system has a different locked rotor multiplier, I'm welcome to use it. Likewise, the asymmetric offset is 1.6 times that locked rotor current. Here's where we're plotting the thermal curve. So let's kind of go ahead and plot this. I've already plotted and saved it, so I can come back and open it up. And it looks a little bare without the text there. But if I go back and open the dialog box, you can see that my thermal limit curve appears because this checkbox is there, and it's being plotted with these parameters from 10 seconds to 200 seconds. Acceleration time was 5 seconds. If we have a quicker acceleration time, we can put in 3 seconds. Expect the motor the acceleration to reduce. Yeah, and then if we have different locked rotor multipliers, now these are used for voltage drop calculations in load flow and for starting curve protection plots for coordination. Okay, so that's motor starting curve. So far we've covered the TCC definitions for transformers and motors. We've looked at the keystone points for transformer damage curves for single and three-phase low faults. And I think that's everything I wanted to cover in this particular session. So if you would please, let's do a little poll question to make sure we're covering the bases. So protective device coordination is a procedure which will do what? So if I didn't lose my polls, okay, let's see if I get this across. So protective device coordination is a procedure that does what? All right, let's give this another 10 seconds. Appreciate your participating. It's no liability, just to make sure I'm covering all the bases. So one of the things that's important to remember is that coordination very frequently increases the arc flash exposure on the particular bus. So you don't want to get confused between mitigation and coordination. It's an issue that will come up frequently when we get into arc flash protection. So transformer protection is critical because this one's kind of a throwaway. Yes, let's give this another 10 seconds. So yeah, the correct answer is all the above, and didn't mean to pull it on you. Probably should have put all the below. But yeah, protective device coordination is critical on transformers because they're expensive and they affect the whole plant. And realistically, you're going to take a long time if you have to replace one. So transformer protection is particularly valuable. And then finally, what is the proper data entry? Why is proper data entry important when constructing a one-line diagram? And this is something I actually want to hammer home, and that is the more accurate, the more detailed data we can collect. And frankly, when you're doing an arc flash study, the data collection portion can be 50% or more of the time involved in doing the study itself. And that's because on older systems that haven't received a study before, it's sometimes difficult to get all the data. So the more data that can be collected, the better job you can do both for coordination and for mitigation. Okay, that completes what we wanted to cover today. Thank you for attending. And by all means, make sure you check out the updates on the schedules for more webinars and training, both online and live training that's scheduled for later in the year. And we look forward to talking to you next week. Have a good day.